Looks like we're now live. We're here with another Infinite Layers, and unlike all of the previous Infinite Layers, we're actually talking with EigenLayer team members. And this is going to be focused on one of the first AVSs, which is EigenDA. So I want to go ahead and let the guests here go ahead and introduce themselves. We'll do a quick introduction into EigenDA, and then we'll dive right in. So Robert, would you like to kick it off?
Sure, yeah. I'm Robert. I'm one of the research engineers at EigenLayer. I've been here at EigenLayer for, going on 3 years now, since the very early days. Been involved in engineering and ideating a lot of the things that we've been building. And since we got started on EigenDA, that's been one of my areas of focus. So taking it from the very early stages of prototyping, figuring out how we are going to solve some of the major challenges in the space, and then on up through rolling it out to production, and these recent days of getting it on mainnet and looking at what are the next steps for the coming years.
I guess Teddy, and then VS next.
Yeah, hi guys. I'm Teddy. I'm a research engineer at EigenLayer working on EigenDA, and I joined about 8 months ago, where Sriram gave me this mandate of integrating EigenDA with various rollup SDKs. So Optimism, Arbitrum, Polygon CDK, ZK Sync, that kind of thing, and doing it securely, which meant getting really into the weeds of how fraud proof systems work and ZK proof systems work, and as well as understanding deeply how EigenDA works from its security model perspective. So super excited to talk about EigenDA today.
Hey guys, I'm Vias, a fellow Genesis block member with Robert, and been on the strategic side and on the BD side since day one, and also been working on EigenDA kind of since the beginning, closely with the engineering team and research team that has led us to this industry-leading product that can support all these interesting and future use cases. So super excited to chat about EigenDA today.
All right, so I guess since we're talking about data availability, what is data availability and why is it important?
Yeah, that's a great question. A lot of sides to that. So data availability, we were talking just now about like what is a better term for it. Because availability is a concept that's pretty ubiquitous and prevalent in like Web 2 settings, right? Just means like we're trying to make sure that the worst case uptime of some service is never below some percentage. So is that the same thing that we mean in crypto? Well, essentially that's the idea, but we're adding a kind of security guarantee on that. So it's not just the worst case availability under some sort of statistical error model, but we need the availability to always be there, even under adversarial Byzantine behavior of the validator set. So that can mean different things, depending on the system. But there are some sort of gold standards when you talk about security for any blockchain system, like economic security, where you would say, we have this property that data is available, it can be retrieved, and that property will always be respected. And if it were ever to be violated, then some attacker would have to forfeit X amount of stake, right? So that's where, of course, like EigenLayer comes into play as the provisioner of shared staking security that can be reused across a protocol like EigenLayer or EigenDA.
Yeah, and just to add to that, I think one thing that really cleared up what data availability was for me when I was learning about EigenDA and various DA solutions was the idea that data availability differs from sort of traditional storage in that it's decentralized and in some sort of certified way. Oh, that's Siri. And then it's also it's transient, so it doesn't stick around forever. The transient aspect is actually less important than the certified aspect, but the transient aspect actually allows it to not pose this sort of ever increasing cost on nodes that are running the data availability service. And due to the function of how rollups and AVSs work, they actually don't need this data to be stored forever. And so we sort of define this new product category, or this protocol category called data availability, to encapsulate those requirements.
Yeah, I think the thing that confused me the most when I first heard the term was I just associated it with data storage, which means I can store something and then I can retrieve it at any time. And learning that it's actually like ephemeral was really blew my mind and made me very confused for a long time. Because like I was thinking Arweave or Filecoin or IPFS, where I can just go grab something a year later or something like that. But I guess like we've talked about like why it's important, but how does it fit into architectures that are being built like in the blockchain world, like modular architectures, rollups? Why is it becoming more of a thing, and like why are more I guess rollups and blockchains requiring and using data availability?
Yeah, well, the obvious application of data availability is rollups, where there's just so much demand for block space right now on L1s, but also L2s that use L1s for their DA right now, that the L1s can't keep up with that DA demand. There's not enough supply, and so prices sort of start to go higher and higher. And so rollups look for a way to scale beyond the capacity of the L1 that they're settling on. And so EigenDA offers this sort of different model from the way L1s work that is specifically tailored to this problem. So whereas L1s have generally like a cap on block size, and they have a block time which determines the maximum throughput of data availability, and where L1s are sort of tend to be more monolithically designed, even if they're sharded out, they're still sort of a central planning of how that works and how that DA scales. Going and using an external DA layer like EigenDA is a way to maybe switch from this sort of consensus-driven model, which we can talk about a little bit more in the future, to a model that just scales better, like structurally scales better, and results in unit economics that sort of stay constant as more demand comes for block space, rather than having a sort of economic model where the DA becomes more expensive the more people use it. So yeah, rollups using DA is the main sort of customer segment, but there's also sort of the possibility for AVSs and various other protocols to use DA to make data available during challenge periods, or sort of during operation periods where that data is needed. And then after that data is not needed, it can be expired.
I definitely want to dive into that a lot more. But before we get to that, I guess, and before we kind of move on to some of these other questions, in terms of like EigenDA, where did it come from, like the idea within the company? Because a lot of you have been here, a long time. And why was data availability what you chose to build as the first AVS, as opposed to maybe letting someone else build it, for example, within the EigenLayer ecosystem as an AVS?
Yeah, I'm actually going to take part of this and leave some of this for Robert as well. But I'm actually going to answer this while also kind of answering the previous question a little bit in terms of the architecture and why it fits in, because I think that really lends itself so as to why we built this first. So we have adopted enough Ethereum users such that Ethereum got really expensive to transact on for all of us. And in order to scale Ethereum, we needed to move to a rollup centric architecture where we could offload some of the computation and execution to these L2s. And so, you know, we started building EigenDA somehow around the same time that Vitalik actually wrote the endgame to Ethereum scaling article on his blog, which was like somewhere around November, December of 2021. And that's actually when the like first early prototypes of EigenDA were being designed, at that time called data layer. And eigenlayer, data layer. But we saw that things got really expensive to do on the L1. We moved these things to the L2, and we also got to benefit from some of the literature and explanation of data availability to the landscape from competitors at the time, because we had started to see the separation of this modular versus monolithic framing, and monolithic meaning these four key attributes of a blockchain: execution, consensus, data availability, and settlement. And we started to see, this transition away from monolithic architectures to far more modular architectures. And now we're at this space of like a truly elastic architecture where people can essentially choose whatever services that they need to provide a unique value proposition to their users on their L2 and connect to any set of modules or services, whether it's in the Eigen ecosystem or outside of it, that just makes sense for their users and their value propositions, right? So that kind of like, architecture that played out aligned with our thesis at the time, which was, in order for blockchains to truly scale, as we move some of these computation elements to the L2 layer, we also need a high throughput, high bandwidth, DA layer to be able to support some of the use cases that traditional consumer applications actually demand, which in turn will eventually help us onboard more on-chain users to the crypto ecosystem. Robert, do you want to take the other half of that?
Sure. Yeah. No, that was a great explanation. I'll just recap like two pieces of that. Like basically, Vyas said scalability was the key reason, because the roll-up scalability pattern handles an aspect of scalability, which is scaling compute, but then you're still left with a bottleneck of scaling data availability. And the way that we look at this is, in a L1 like Ethereum, it's unscalable because any compute that you need to do is going to be replicated across all the nodes. So the cost of doing, one operation is going to be multiplied n times. Same thing happens for data availability. Since every block is being sent to every node, there's like this complexity in the cost that's very highly undesirable. So rollups take care of the computational complexity, but how do we deal with the complexity of data availability? We wanted to try to get it down to this like order one complexity, so that any data that you want to make available really only needs to be the cost to the network is really just on the order of the size of the data, instead of on the order of the size of the data times the size of the network. So following that sort of roll up scalability pattern where we're getting it down to a constant order. So how do we do that? When we looked at the other architectures that were being considered in the space, none of them actually achieved this property. So it was sort of an ambitious idea. And we went back to the literature and kind of looked into this idea of essentially using erasure coding to shard the data across a network of nodes. Erasure coding is well represented in other architectures, like proposed architectures for Dank sharding and Celestia, but it's really only used for something called data availability sampling. And so we actually kind of expanded on the usage using erasure coding as sort of a core ingredient of the architecture for doing sharding of the data, which gets us back to this sort of like ideal constant order cost to make data availability. So that was the central theme of the design direction there. And since we were starting with, our starting point here was EigenLayer and the concept of an actively validated service, we were also able to shed a lot of complexity in the design of a new protocol along the way. So what kind of came forward was a very simple but powerful idea for how you could get scalable data availability. And we've been kind of tweaking that and adding improvements over time. But in the early days, people asked us, how in the world did you create this prototype in 3 months? Like, who built the P2P layer and all this stuff? And we're able to say, well, this is the beauty of an AVS architecture. You don't actually need many of these ingredients that are typically present, like a consensus protocol, P2P network, and so forth.
This is also us having a world-class research and engineering team with multiple PhDs or people who were pursuing PhDs in distributed systems and peer-to-peer networks. So like we were building with a team of like studs at the time. Like, let's just make that also very clear.
At the time and still. So I guess like from a proof of concept to now, it's taken, I guess a year or something like that to get it to where we are now. What is the current state of EigenDA for anyone that isn't up to date real quick?
Yep, we're running on mainnet with 10 megabytes per second capacity across 2 quorums. So we're secured by ETH, staked ETH, and Eigen at this point in time. So that's sort of the product is delivering the essential feature set, and in the coming months we're going to be adding things like payments and data availability sampling and so forth. Teddy and Vyas, anything you want to add to that?
Yeah. So that covers it. I think on the integration side, EigenDA has supported a few different POC integrations up until today, actually, where today we launched the OPStack official Alt-TA integration. So, for those who are unfamiliar, OPStack is the software stack that powers Optimism and Base and several other L2s. And until today, we essentially recommended that any rollups that wanted to use EigenDA, either in testnet or mainnet, would have to fork Optimism. And that would present long-term challenges when it came to compatibility, and often sort of made people a little bit uneasy. Like, are we going to consistently maintain this fork? What's going to happen? And so we're very proud to say that we're officially integrated with this this interface that should be maintained for a long time and should result in a very secure and sort of like trustless integration with EigenDA. That's for OPStack. Arbitrum Orbit, we are supporting stage 0 integration, and we have a few other sort of POC integrations with CDK and Rollkit. So yeah, I think that we are finally getting to the stage with EigenDA where we are completely open for business and onboarding rollups.
In terms of the product itself, like the differentiation of EigenDA, some of the things that we talk about often are hyperscale. We talk about the cost efficiency and things like that. What does that actually mean? Like, what does hyperscale mean? How is that different from other data availability solutions? And what are some of the unlocks and use cases that we're seeing so far?
Yeah, so hyperscale is sort of the other side of the coin of getting the complexity right that I alluded to earlier. Our solution, you could say, is horizontally scalable. So that means that any additional kind of unit of computational resource and network resources that gets added via a node joining the network is going to extend the overall capacity. So you can see how that quickly adds to an aggregate amount of capacity that could be sort of arbitrarily large, right? As you horizontally scale. How does that compare to other solutions that are out there? many other networks have sort of a concept of a full node and a light node, where the light node is sort of the gesture towards scalability, in the sense that like I can participate in a network in a way that helps augment and reinforce its security without being a full node. Now, what is a full node? A full node is usually a node that kind of more or less processes on the order of all of the data that's sent to the network, although there are some variations on this. So when you have that ingredient in your system, what kind of scalability do you have? We call that vertical scalability, because it means that the node needs to, that full node needs to be able to scale to accommodate the full throughput of your data availability layer. And vertical scalability is sort of just a different animal, right? If you're claiming that you want to get to a gigabit per second or whatever these long-term use cases might require, that means that every staked node in your system needs to be able to support that. And that's going to mean much higher costs, much higher operational complexity, which will drive toward centralization, which again puts a lot more pressure on the light clients. So it's sometimes difficult to see how these architectures really can evolve to that future world where we are talking about true hyperscale, gigabits per second, bringing Web 2 applications into the Web 3 world. And that is sort of the use case that we want to unlock here. Anyone who has built in crypto has come to find themselves in this mindset where any kind of trivial operation that you would do in a Web 2 world, you start realizing like, oh, that's not possible here. We need some clever workaround, right? Bringing things off chain, or just simply not even building the application that you thought you would build. And in order to get people out of that mindset where they can say, here's something we have in Web 2, let's just make it secure and decentralized and put it on Web 3, you need scalability, you need data availability and execution that can just simply scale and grow to accommodate all the use cases that come along, right? So that is, in a nutshell, is the hyperscale idea. It comes with a lot of, that there are different sort of dimensions and layers to this. Obviously, like the first barrier or bottleneck that's going to show up for a lot of people is like the economics, because markets have to be built in order to accommodate a fixed amount of throughput that's available on an L1, for instance. So with EigenDA, what you'll see is that as we push toward hyperscalability, we're reimagining and reformulating the economics of data availability. And that shows up in new ways of thinking for developers, where they can, for instance, say, okay, we're going to actually, we know we have this throughput. We know that data availability is there to solve problems. So we can actually pay a reservation for the next year to have all this throughput available. And we don't have to worry about escalating marketplaces and gas prices increasing. And so, in a lot of different ways, hyperscalability is just the necessary next step to enable all these amazing use cases. And I'll stop rambling there if anyone else wants to add something.
No, that was great. I think like when we talk about high throughput, we're talking about essentially more TPS and keeping that TPS low. And I think like I know that these transaction numbers are often very nuanced, because like what type of transaction is it? But I do know that we have had rollups building on EigenDA that are hitting like 100K TPS already. And we are still like orders of magnitude lower than where EigenDA will ultimately be, even by the end of maybe this year. So that's kind of exciting. And I think like talking about numbers like that makes it more, understandable maybe for someone that might not have actually built in this space. So we're talking about, like if you're building a roll up and you want to have a game, or you want to have some type of so like pump.fun, right? There's like millions of people like using this app, or maybe not millions. Let's say there's probably like thousands of people using this app at one time, and they're all transacting. You can't really handle that on a lot of EVM equivalent L2s or rollups right now. So how could we enable 100K TPS? So this would be one of the pieces of that puzzle, right?
Yeah, absolutely. I think we're going to blow by the state of the art when it comes to TPS and scalability once DA solutions like EigenDA start to get integrated into applications that users really want to use. It's going to be, going from a model where, you have a certain number of lanes on the highway, and so, there's only so many people who can use that highway for any unit of time, to a model where it's a little bit fantastical, but the highway gets built as people need more of it. So yeah, we're going to essentially have a situation where I believe that L2s on Ethereum will develop this reputation for having greater scalability than even Solana, which has this pretty good scalability story and narrative. I think it goes down a lot under really high load, but I just looked at the dashboard and it does 3,000 transactions per second. I believe that L2s using EigenDA will regularly scale to hundreds of thousands of transactions per second. And this is sort of this amazing future that we have, that we get to work on at EigenDA, and kind of get to believe in. And it makes me very optimistic about blockchains in general, especially in a time where sometimes it feels like the industry moves a little bit slow. It feels like we're right on the cusp of sort of a new era for blockchains.
I couldn't agree more. I think we're hitting that the way my brain wraps around some of the architecture designs today. We're back to something very akin to Web 2, where developers can go and integrate with whichever SaaS modules they need to solve whatever use case that they might have. If you need to sign in, you have OAuth. If you need to pay, you have Stripe for your payment processing. You need to install some sort of like analytics layer. Cool. You have like multiple different SaaS modules that can do that for you. Right. And similarly, we've started to go to a very, modular, very elastic design space in the services that can be built for decentralized applications. And, Teddy touched on TPS, which is one dimension of showing like what is the use cases that we're capable of, right? It's a very like financially driven dimension often, because like Solana is predominantly a DeFi chain. DeFi applications are still like the dominant use case for crypto today, and TPS matters the most to that audience. Simultaneously, we have other use cases that are propping up, and SocialFi, similar to DeFi, still relies on like high throughput necessities. And so, that transaction data, rather than being financially driven, becomes now socially driven. And, maybe the value for security, crypto economic security, may not be as high, but the value for throughput is extraordinarily higher sometimes from the social chains or gaming chains even. I think in addition to TPS, which is that one metric that is easy to wrap our heads around in terms of how fast we're scaling, we also need to start thinking more about, okay, what are the new use cases being enabled by this levels of throughput as we try and scale to what we want to aim at 100 megabytes per second, hopefully by the end of this year. What are the use cases that can be enabled by a system that's fully decentralized that can handle that level of throughput? We're already at the point where we could theoretically support lossless audio streaming at 10 megabytes per second on EigenDA, and we could, theoretically run this. What does it look like when we're at 100 megabytes per second? What does it look like when we're eventually at 1 gigabyte per second? And now, how can we, remove this almost rut that crypto developers have been in for the last couple of years, because they've just been so restricted by block space and so restricted by the system requirements that you end up with this cycle of loss of creativity that leads to this kind of toxic feedback loop. Now let's try to break them out of this and kind of reinvigorate and re-inspire what are the creative ventures that could be enabled by this surplus throughput.
Yeah, this is exciting me a lot because I think one of the first things that I became a little bit, I would say, I don't know, when I first learned about the whole paradigm of Web3 and how you can kind of use blockchains is the way I was looking at it is like a database. Like anyone can interact with it, anyone can build upon it. It's very composable. And then I started throwing out all these ideas that I had, and then the person that I was talking to at the time was Yaniv, the founder of the Graph, who had brought me in there. Was like, oh yeah, by the way, like we just can't do that yet. Like it just doesn't. It's too expensive to do that, or we can't do that much throughput. There's just so many things that you couldn't do that I became a little bit depressed. I was like, okay, well, this kind of sucks. Like, what can we do? And we're always like, from that point on, trying to kind of hack and find workarounds to make things work. And but being able to kind of get closer and closer to the type of throughput that I was used to at AWS, like DynamoDB, right? 100 million operations per second we were seeing for certain applications. Going from that to at the time working on ETH-L1 was like a night and day difference. So I think with this, we're getting closer to that type of scalability. And think you mentioned that horizontal scalability versus that vertical scalability. I think we're getting to the point where those two things are being combined, right? We have these roll-ups that are essentially app chains that are plugging into all of this infrastructure. So you have application-specific block space that can plug into this more horizontally scalable block space. But and before we get on to my next question, this is going back a little bit, and this is maybe a little basic for some people, but for those that don't know, what is the data that's getting written to the network specifically? What type of data is that? Is it restricted by a certain type of data, or can you just write anything there?
Yeah, so when you submit a transaction on MetaMask to some L2, let's say it's Base, you're sending that transaction to a mempool in the sequencer for Base or Optimism's sequencer. And there's a component within that called the batcher, which when the batcher is using L1 for DA, it's just sending that transaction to the L1, and it's just writing it to the L1's to some data field within a transaction that's not going to a contract at all. It's just being persisted within the consensus of the L1. When you go and use, or when you're using an L2 or L3 that's using external DA like EigenDA, the batcher component of the sequencer is actually writing your transaction along with a lot of other transactions in the batch to the DA network. And then it's getting back something called a DA certificate, which the batcher or the sequencer then posts to Ethereum or the L1 where the settlement is occurring, instead of that big batch of data. So the DA certificate is something on the order of hundreds of bytes rather than on the order of hundreds of kilobytes or megabytes. And this is where the cost savings occur and the throughput increase occurs, because one DA certificate can represent a kilobyte, or it can represent a megabyte. It could represent a lot of data, and so you don't have this sort of bottleneck on how much data you can write to the same degree, and you also have this great savings in cost. The rest of the rollup operates the same way. So when it's reading, or when it's deriving, as they call it, it's looking at Ethereum for what DA certificates have been posted, and then it's taking those DA certificates and using them to look up the transaction data from EigenDA. And then from there, it actually executes that data into state routes, which it posts to the bridge. So the whole process is oriented around transactions and increasing the number of bytes of transactions that can be processed per unit time.
And then if someone wants to then read data back from the network, they're passing in some type of ID, and then you would kind of compare. Well, like, what would you compare this if you were using like a typical database as an analogy in terms of
Yeah,
like a
sure.
lookup?
So the DA certificate corresponds to the primary key in a sort of database analogy, where you use this DA certificate not only to look up the data from the database, but you also use it to verify that the data is correct, which is sort of where that analogy goes a little bit different, because typically in a Web2 database setup, you're trusting the database. You know that the database is going to give you probably the correct answer, unless there's something very wrong with your system. But with blockchains, that's not good enough. And so the DA certificate not only has information on how to retrieve the blob, but also how to verify the data that is returned from the network once the blob is retrieved.
Mm.
And then finally, it also has the information to be able to certify or to verify that the blob was actually stored by the EigenDA network. So you're not just sort of making some requests into the ether and saying, hey, store this data, and then you get some a DA search or something that looks like a DA certificate back, and you say, oh, this looks legit, and then you pass it on. There's actually a stage where you're verifying that all of the different operators within the EigenDA network actually did store the data or certified to store the data, and you can do that using asymmetric encryption and sort of signature verification. So yeah, that's the full analogy compared to a database.
So we have about 5 more minutes, and we're going to wrap it up with 2 more questions. Ethereum has already moved to like this roll-up centric roadmap, and there are now EIPs that are kind of moving us in that direction. We have 4844 and dank sharding, and we've already seen progress in that direction. What would be the main trade-offs between using Ethereum itself versus using something like EigenDA for your DA at this point in time, and maybe in the near future?
Yeah, great question. So I think one thing that we see with EIP 4844 is that, because Ethereum in sort of any version of the roadmap is still not horizontally scalable, they're going to have a fixed upper limit on throughput. And so how does the system, from an economic standpoint, handle that fixed cap? Well, they need to have some kind of economic mechanism for allocating that space, right? And for EIP 4844, it's sort of a EIP 1559 style escalating price mechanism, so that once the space becomes congested, prices will increase until that congestion becomes manageable and the desired amount of space at that price fits snugly within what's available, right? And so what that means is that you can have sort of a phase change between the world where demand is less than capacity and prices will be very low, and the world where demand exceeds the capacity, very roughly speaking. And if there's enough demand that's high in value, then suddenly the price will jump up to the value of the last sort of transaction that is going to fit into that space, which could be quite high. So when you reach this phase change, so suddenly like your cheap data availability can vanish. And really the only way to eliminate this dynamic from a system is to ensure that you can always keep capacity well beyond the high value demand. And our kind of perspective is that this requires an architecture like EigenDA. So for EIP 4844, rollups that are wanting to use it might see reasonable prices now, but there's sort of an expectation that those prices will increase quite a bit over time. as more people start to vie for the space. We're confident enough with EigenDA that we can stay ahead of the curve, that we have a pricing instrument called a reservation, which allows rollups to lock in a price for like a 6-month period. And this is something that like EIP 4844 simply cannot do. But we see it as a big advantage for rollups that want that pricing stability, so that they can maintain viable unit economics at a given level of throughput. There are related features on the economic side that are sort of more available for an application like EigenDA, given that it is an AVS, and there's some level of non-neutrality in the economic side that's available that wouldn't be available to an L1 protocol. And what I mean by that is we also enable rollups to pay in other modalities than ETH. Like if a rollup has a token, that can be a direct sort of negotiation between the operators and the rollup itself for like what is the rate at which we'd be willing to accept this other payment modality in exchange for the data availability service. That can be a big advantage, and just a striking difference in terms of what the economics look like for a rollup customer compared to EIP 4844.
So to wrap up, I had one final question, but I think we've already touched on it, and it was basically, what are all the different features that would make EigenDA specifically appealing to a specific customer persona, or especially appealing? But we've kind of talked about all those, but can you all kind of maybe summarize all of those things into like, 1, 2, 3, 4, just to kind of essentially summarize this whole conversation, but also the value prop and the differentiation of EigenDA?
Yeah, in some ways, like all the different things that we have been talking about are just all of the different pieces that need to come together in order to give you one very simple thing, which is like stable, cheap, and secure data availability. And that's sort of how I'd put it, but maybe Teddy and Bias can add some color and nuance to that, or maybe a 1, 2, 3, or a 2, 3, or 4.
I would no, I totally agree with you, Robert. The way I think about it is just for builders, we need to go to a landscape where speed is no longer a constraint, cost is no longer a constraint. Specifically the cost to tinker, because I think that's the most important thing for devs in the beginning. The cost of tinkering needs to be like non-negligible, and then the cost of usage eventually should only be like rational based on your amount of usage. So again, speed shouldn't be a factor, cost shouldn't be a factor, and creativity shouldn't be a factor. Like we don't want to put any limitations. We want this to be like as as open, as free, and as performant as possible. And as we continue to increase the number of nodes, we bring our costs down and we bring our performance up, and we continue to scale to like push the barrier of what's possible, and eventually just onboard more consumer use cases.
Well, that will go ahead and bring us to a close. I work with you guys every day, but I learned a lot. So I'm hoping a lot of other people that have watched this have also learned. If you missed any part of this, it's going to be on our YouTube later today. So you can just go to the EigenLayer YouTube by Googling EigenLayer YouTube, or maybe go to one of our social accounts. We'll also share that. But I appreciate everyone's time here, Robert, Teddy, and Vias, and everyone that chimed in or tuned in to watch the stream. I appreciate your time as well. And we will see you next week with another Infinite Layers.